Where's my share screen? There it is. Okay, can folks see that okay? All right, so welcome to the May 2023 meeting for Seattle Robotics. Steve is here, but he's a little jet lagged, so I'm going to go ahead and continue to fill in. Pretty much kind of the normal schedule. Let's see, kind of do all the normal stuff we do. First off, the video is provided by Zoom. We're going to record this and we'll post it on YouTube later. There's kind of the standard agenda for today. Pretty much same thing we've been doing for I don't know how many years now. Please mute your microphone unless you're actively sharing something. That will keep all the background chatter down. Hopefully folks can hear me okay. You can use the Zoom chat to ask questions and comments. We'll also capture that and post it after the meeting. So the new First WA venue, we're still working on getting that set up. The address is shown there. It's in Kent. We might do this in June. We might do it in July. I don't know, Steve. We still need to reach out to Kevin and find out what's going on with that. Donna and I were talking about being able to go down in June at some point, and take a look and see what we can do for getting hybrid set up. So folks that are attending remotely, well, it's all of us right now, but even when we do go back to the in-person meetings at the new facility, we will keep doing hybrid. So I've got another slide on that later. Oh, that's actually it right there. We do need another 1 or 2 people to help out when we do that. We're going to have to run a video streaming and setup and computers and cameras and so forth. So I'm going to help out. Donna's going to help out. We'd like to get a couple more people. So if anybody's in the area planning to attend in person on a semi-regular basis, it'd be really good to have some backups. Past events. Does anybody know how the PopCan challenge went? Wait, Chaz, you might.
Yeah. Definitely know how it went. It was a great venue. We had a lot of fun. So it was the first weekend of this month, and it was amazing. John actually was able to complete the entire PopCan challenge for the first time ever in a competition. So congratulations to John.
Nice.
We do have like kind of a gentleman's agreement that there was like a deduct for time because his robot couldn't do it in 5 minutes, but I think we're going to try to make that part of the standard rules. And Greg came up right behind him. His robot just missed the table a little bit, but it was pretty amazing. So it was John first place, Greg second place with Gidget. Robo came Gidget, and then my robot came in third, and then Auto Dave was fourth place, and then there was 2 other robots at the session that didn't compete. So one was my actual PopCan challenge robot, and Terry had a robot there. So, but it was a great time, and I think we're going to do it again in October at the Maker Fair that's up in Everett. So yeah, good times.
Cool, thanks.
Yeah.
So speaking of upcoming events, RoboMaster NA, I'm not sure what this is. That's July 7th to 9th at the UW Hub. There's a robot event website for national events. And Robo Games is back in Pleasanton, California. I think they were off for a couple of years. And of course, there's always meetings at the Snowco Makerspace.
It's actually, can you guys edit that? It's in South Everett. It's in Snohomish County, but South Everett.
Oh, okay.
Yep, thanks.
I'll let Steve handle that one because
Whenever, yeah.
These slides.
Of course.
Okay. So we do have another couple events coming up this summer for Robothon. So the Robothon virtual exhibition number 4 is June 10th Last I checked, we're still looking for a couple of presenters. So please reach out to Donna if you'd like to present at that one. That will be, we're going to do noon to 3. That's coming up really, really quick, actually. So if anybody would like to present, please get in touch with Donna quickly on that one. We are also going to go back to a in-person event, RoboMagellan Plus, September 9th. That will be at Sunnycrest Elementary School. So this will be RoboMagellan. We're going to have the new robot challenge there, or the new SRS challenge. We're going to have, I believe, line maze and sumo as well. So it's going to kind of be a little mini outdoor version of the full Robothon event. So that's coming up on September 9th. And I'll give Steve's general plug for presenters. Steve is always looking for presenters. He's actually doing pretty well. He's got a pretty good roster coming up, but
Sorry.
hey, Steve,
Yeah,
I'm begging for presenters for you. Would you also like to beg in person?
yeah. So I think I believe we're booked either through October or no, I think through October. So I think need a couple more to close out this year, and then we'll be good till end of the year. So yeah, if you just send stuff to the email on the screen there, and keep them coming towards me, and then I'll just reach out to them and see what we can do. So take it back.
If we don't have any particular speaker, Steve also has a list of open discussions. And so we'll pick off one of those and go. We did Chat GPT a little while ago, and I think we did one other one. But we can always do one of these. And here's the list. So hey, Chaz is in there. So today we have Charlie. I'm not quite sure how to pronounce your last name. Xiao. With the
it's like shower without the ER sound.
Okay, thank you.
Yeah.
So we'll start that here about 11 or so, depending on how we're doing for time. Kind of feeling like we might be a little bit ahead, but we'll see where we're at. Yep, as Steve was saying, we need 2 more for November and December for this year. And let's see. Oh yeah, feel free to hang around after the meeting. I'm going to have to disappear right about 12 o'clock, but I'll hand off the meeting to someone else. We'll stop the recording, but folks can hang around as long as they want and continue to chat after the formal presentation. And around the room. Okay. So I'm going to stop sharing, and who has something they would like to share?
Are there, it sounded like there were people that were queued up there on that slide. I don't want to jump in front of anybody.
Let's see. I got to check the chat real quick. Hang on. Nope, I'd say whoever wants to go, let's just do it.
So I have something I want to share that is robot adjacent.
Okay.
So
you want to turn your camera on, James, and I can spotlight you?
Oh, you don't want to see the camera turned on, dude.
Okay.
It would be bad. Is it okay if I just share my screen there?
Yeah, no, go for it.
So this is, and I'm also going to post a link in the chat.
Not quite seeing your screen. Yeah, there it goes. Took a second to
Yeah, it takes a little bit of time sometimes. Anyway, if people want to look at this on their own, the link is in the chat. It should just share with them. Okay, so what this is about is machine learning, and that's applicable to robotics in a lot of ways. But I've been teaching these classes, and I'm trying to figure out how to get across the idea behind machine learning to like people who have a high school level education and maybe aren't that crazy about math. Because basically, you know, all of the machine learning neural network stuff is super heavy in math. So I have this web page, which is actually linked at the bottom of the source code here. I'll show you that just really quick. Well, actually, maybe I won't. Only because I think I'm sharing my tab right now instead of sharing my screen, and I should have shared my screen. Anyway, I have previously written this this TechRef link about linear regression, but it's really heavy on math, although it tries not to be. But it makes the point early on that most of the matrix math and the neural network weights are very related to this basic idea of, you know, y equals mx plus b, the old, you know, linear formula that everybody learned in high school. And that's hopefully simple enough math that people can like get it. So what I did was I am using this StackBlitz site, which allows you to host like a little website just for development purposes. And you see the files over here. You can edit the files in the middle, and then you see the result over here. And if you want to refresh the result, you get, you know, you can get a new run of it each time by doing this. And basically what we're doing here is you can kind of see like there's a fine red line here along in kind of in the middle of these points, and I'm randomly coming up with that slope and offset for that line, and then I'm randomly making a bunch of points that are above and below the line, you know, offset by random amounts. And the idea here is to pretend that those red X's are data that came in from the outside world. And then I'm starting off with a line as a guess that's just a standard straight line. It's actually this first one here. And then I'm taking and doing the distance. So I'm taking each one of these points and pushing it onto that line. You can see the little tick marks there. Every one of those is one of these X's projected perpendicular onto that line. And then I'm measuring the distance of that projection. So in other words, how much error is there? And then from that error, I'm figuring out how much to change the slope of the line and how much to change the offset of the line. The offset isn't working fantastically, but it doesn't have to. And it kind of being wrong is sort of the point here. That's not a bad thing. But the source code, if you read through the file in the middle, it explains all of this. It goes through and explains everything and shows how like the line is being drawn, how the graph is being drawn, how we're plotting linear formulas onto the graph, and then how we're generating the points and how we're figuring out how the points intercept the line and figuring out the error by figuring out the distance with hypotenuse there, and so on and so forth all the way down through. And then we do, finally what we do is this part where we're actually trying to adjust the line in order to make the line, the guess line walk onto the original line, or try to draw a line through all the points. And obviously there are much better ways to fit a line to a set of points. But the point here is that this shows how neural networks do it when they're adjusting the weights in order to fit a multi-dimensional line onto something for linear regression. So anyway, it's supposed to be like a preview before you actually read this page, which really goes into how a linear regression works with, you know, it goes into like gradient descent and all that kind of stuff. So the reason why I'm showing it to you is because I would absolutely love to have some feedback from people. And like an idiot, I realized that I didn't put my email address in here. So I will just add that really quick.
Yeah, I think that the one thing I ran into is, you know, when you read the actual literature on, you know, neural networks and so forth, it was backpropagation was the one that always drove me insane, and it was basically not because it's necessarily that hard. It's everything I read early on was done in a very mathematical, very abstract, very generic way. And so somewhere along the path, I came across something that basically did something similar to what you're doing, but they were still looking at the derivative, but they took one transfer function, a simple one, right? With a simple threshold function, did the derivative and left that as a constant. Like, here's the derivative for this system, and then just walked it back and was like, oh, that's all they're doing? Yeah.
Right. Right. Yeah. If you happen to remember where you saw that, I would love to try to link to that, because you're absolutely right that all of the explanations of how neural networks work are so math heavy. And I understand that I mean, they're based on math. So it's super hard
Yeah.
not to be math heavy. But if you can gain an intuition about how it's working, then suddenly the math can start to make sense. And
Yeah.
before you have that intuition, you're kind of dead. So anyway, I just wanted to share that, and I would be deeply, deeply honored if anybody in the Seattle Robotics Society had any feedback on that page or on the.
It was a couple of books. Hang on, let me see if I can grab them real quick.
You're a gentleman and a scholar. I don't want to distract you from your
That's right. We got time, so.
duties, but yeah, if you find that. So and just so you understand, the reason for this is, well, number one, I honestly really feel like you don't understand something until you can teach it to somebody who doesn't understand it at all.
Yep.
At that point, you really have a grasp of it. So this is my ongoing attempt to really understand how this stuff works. And then secondly, you know, I'm trying to do more, you know, like mentoring and working with people, not necessarily kids, but like people who are interested in getting into this, you know, business of robotics and the artificial intelligence. And also, I'm getting ready to teach this UCSD extension class to a bunch of high school students. So it's a remote learning thing, but still, it'll be an interesting class. And trying to make sure that they can actually get this stuff is really important. The other thing I would really love to see any examples of is like how, okay, so let's put it this way. I've seen, there are tons of people who took like out of the box, quote, artificial intelligence or machine learning systems, like, you know, object recognition, and just tacked it onto a robot and, you know, oh, hey, I did, you know, that. I'm not looking for that. But if somebody has done anything where they've been like, you know, my torque motor curve or my wheel slip loss of friction issues seem to be following a pattern here. I could train a neural network to predict that and help me to control my robot better. Or, you know, I don't know, something in that sort of thing where it's not just like a canned out of the box thing, but something that used hopefully at a basic level, the basic idea of training data and having the robot then learn to adapt better and better. I would just utterly love a reference to that. So that's my whole deal. Thanks much for listening.
Well, one of the places where you can go, there's a video by Andrew Ng from Stanford talking about linear regression using neural networks and also doing recognition.
Yeah. So that web page that I'm directing people to at the bottom of it is basically my crib notes from taking Andrew Ng's class. So,
oh, well, I thought it was pretty straightforward.
I shouldn't have said that on the recording, should I? But I don't think he minds if people, you know, use his stuff. Yeah, I thought it was pretty straightforward too, but it turns out that the math really messes a lot of people up, even that basic level of math.
Oh, okay, because I've built neural networks to do recognition.
To do what kind of recognition?
Recognition of whatever.
Okay.
So one of the sample problems I had was some wines, and the idea was to pick between 3 wines given a set of characteristics. Then you train the neural network, and then it you put in the characteristics for an unknown wine, and it picks one of the 3.
Awesome. Did you share that anywhere, like GitHub or something?
I have not. I have it on my computer somewhere. It'd take me a while to find it. That was years ago.
Oh, geez, Bob, that would be awesome. That's just exactly the sort of application that I'm looking for. If you can dig it up and put it somewhere, I would be ever so grateful.
Yep. Yeah, I'll see if I can find it.
Hey James, I dropped it into the chat. The book,
yeah,
pretty sure this is the one I ran across. It's a series of 3 books. They're like $10 a piece on Amazon for Kindle version. It's called Artificial Intelligence for Humans, Volume 1, Fundamental Algorithms. And
Awesome.
he takes I'm hoping I'm remembering the right book, but I'm pretty sure I am. He takes a very simplified, intuitive view or approach to describing what's going on, and he approaches the other thing I got out of this that was interesting is he approaches the neural network. He kind of goes through the simple regression, linear regression, kind of builds up to it. But by the time he's done, he approaches the net implementation of the neural network as a universal function, which I also thought was highly intuitive and very very insightful. So there's a couple pieces in that book that I think really kind of break it down and make it a little more obvious what's really happening.
Thanks.
And
I'm
it's a series of three.
adding that.
Go as far as you want with it.
I'm adding that as we speak. Appreciate it much.
Okay. Was that all you had, James?
That is all I have.
Okay. Who else has something? We got about a half an hour to fill here, so somebody come up with something. Let's see. So if that doesn't work, we've got some videos that Steve put into the chat, so we can do a couple of those. Do we really have nobody else that wants to share something?
I can share a little bit about my pop can challenge endeavors.
Oh, go for it. Yeah.
So in November, we did the pop can challenge at Lake Forest Park at a bookstore there. What was it called? It was the Third Place Commons.
Third Place Books.
Oh, what was the name of it?
The store is Third Place Books. The area is Third Place Commons. It kind of goes by both names.
Oh, okay. So anyway, one of the challenges I had there and before that was having Ross communicate between my robot and my laptop, and I was having problems with RF interference with all the cell phones and everything going on. So what I did this time was I changed my Raspberry Pi on my robot to a Raspberry Pi 3B Plus, which has 5 gigahertz ability. And then I used a router, and I put the router really close to the arena. And then I got this app, and I'll put it in the link. I'll put the link in the notes here. But the app is what's it called? It's a Wi-Fi analyzer, and it's in the Google Play Store. Let's see here. It's this one. Anyway, with that app, I was able to find really easy. It just shows the least congested channel right there. I just used that channel on the router, and it seemed to be helping a lot. So I was able to actually run the robot without too much problem at all. But that analyzer would be good for anybody that wants to get a good connection where, like in an apartment or whatever, you want to find the best connection.
So that's really valuable for like anytime you go to a show or a maker fair or any of that kind of stuff. The other one would be some kind of light analyzer if you're using any kind of light sensors, because your robot with like line follower or whatever always works perfectly at home, and then you get it to the actual place and the lighting's different and nothing works. That's cool. Thanks. I would be really curious to hear lessons learned from any of the PopCan Challenge competitors.
Well, I know one of the other issues both myself and Greg had was seeing the refrigerator. He's using a camera, and I'm using LiDAR, and I can't speak too much on his case, but with mine, the refrigerator was so reflective and dark. I was not getting a good reflection off of there for the LiDAR to actually read the face of it. So so I couldn't find the edge of it using the LiDAR. I ended up just coming off the wall, scoring up to the wall next to it, and just bringing the robot out to its the measurement that I needed to, and at the place I needed to be, without even using the refrigerator.
Just dead sticking it after you found the wall.
Yep.
Or, yeah, you know, that's such a great point. One of the things that I think people run into all the time is that if you're using a system that a human being can't debug, then it's really hard to debug, right? So, you know, like using binary protocols or using, you know, alternate light sources or working in infrared or any of that kind of stuff, if you don't have a way of visualizing it, it can get really tricky. So I wonder if there's a way of visualizing LiDAR other than, well, I guess what do? You just plot it on the screen then, right?
Yes, it's got it just measures all the points surrounding the object that, you know, where the LiDAR is. But unfortunately, when you have something like a reflective surface, it's not going to get a good reading.
So I have one. If you're done, John, I don't know.
Yep, I'm done. Thanks.
Yeah, no, thank you. So I took a page out of David Anderson's book. David's part of the Dallas Personal Robotics Group. I think that's their name. And if you ever, I've shared it before, or somewhere I've shared it before, but he has a really great video about, I mean, I wasn't using necessarily how he programs his robots, but he uses subsumption, and but his robots all have kind of like an on the robot way of manipulating the robot's mode, if you will. And I have a way to suppress in my, I switch between states, and my robot runs off state tables. And then it just runs loops through each state, right? And if it's like, if this is true, I run it. If it's not, I keep on going. Like, has this finished? No, keep on going. And so I was able to like quickly troubleshoot my robot. I didn't get a lot of, well, certainly didn't get as much test time as I should have gotten beforehand, but being able to like go through and suppress certain, you know, modes, turn them off, I was able to like really quickly, and I probably stole a whole bunch of extra. I mean, I'm guessing I ran like 10 times the number of test runs everybody else did while we're there, just because I was quickly able to make changes. And it's all just like right on the little, you know, display. You know, I'd have a little rotary encoder push button, and I could just go through and like, you know, select which mode. Actually, that robot has the 2 Seattle robotics challenge, the build challenges built into it, and then Robothon. But I can go through the Robothon competition and like disable certain modes. So if I just wanted to test one section of it, I could put the robot where I think it should be, and it can go and say, okay, you're in front of the wall, start moving, and then, you know, try to wall follow. And so I could just have it do that portion of it without having to like re-download the code. And I could just test these little sections of the different modes the robot would go through. And that helped me out a lot. It helped me go, and I mean, we only had 2.5 hours or so of test time, and it was just really nice to be able to quickly go and test just a portion of its functions. So if you're building one or one of the build challenge robots, I highly recommend that.
Chaz, how did you enable that modularity in your code? Out of curiosity.
So wow, this is a whole conversation for sure. So I have a master state table, right? And I switch between master state tables based on whatever challenge it's going to be in, right? And right now I have 4. I mean, it's hard coded, pre-built for 4 different challenges. It's got the 2 SRS builds a test and then the PopCan challenge in it. And so it puts it into one of these master state tables, and it runs through the state table, and it says the first one it's whatever the discrete functions of the course might have. So in this case, it might be start moving against the wall in the PopCan challenge, right? And then turn 90 degrees towards hull, approach hull, and then it'll keep looping this through until that activity has been acknowledged as done, and it'll pass it on to another task manager of sorts. And the task manager actually, it does a couple things. It actually goes through and it says, how do you hit this milestone, right? And until it says true, it keeps doing that, but it'll go through the main code, through the entire set of the main code. So I can do things like task management. For instance, in the test modes, I was getting, I felt like it was a PID loop issue, but it turned out like the side-looking IR sensors for distance take a really long time to report back. Like you ask them for the data, and it's dozens of milliseconds in some cases, which is a huge amount of time when you're trying to run some loop code. So I didn't know this. I couldn't know this, because like James mentioned, like it's hard to visualize in your brain. You just see a problem with code. And I found that I have a task manager that I can sit there and see how long it takes for the robot to complete certain tasks. Kind of like you see a task manager in your computer, right? You see all your processes and it sorts it by whatever is taking the most time. So I can see, can I fit anything more in this? And I write all my robots with those task managers, because I've run into this problem, or like an IMU that's just not giving you, or it's airing out a lot or whatever. It's come in handy a couple times for troubleshooting, but I can share the code with you. I mean, it's not top secret by any means. I don't care if somebody wants it. I do actually.
I would love to see that code as well.
Yeah,
you
I'd
want
just like
my
to see the example.
Yeah.
I think it's fantastic that you worked that out, and it made it a lot quicker to be able to troubleshoot stuff on the course, because even when you have a whole day, our time is still limited on how much time that people have to prepare for the events.
Yeah.
And it seems like it's always too short.
Yeah. I will warn you, no problem, throw it on GitHub so you guys can see it, but I am no software programmer. I write like PLC professionally and C code. Like I started in assembly, and C is still like, I'm not a great programmer. So thank heavens I don't do it professionally.
Yeah.
So
And
that's
C code, right? Just straight C code.
It's all C. Yeah, it's all Arduino. So
that's
it's
beautiful.
Yeah.
So really quick, 3 things about the first one is this whole thing about sensors being really, really slow. That I run into that all the time with vision systems. They're super, super slow, and people don't realize how hard it is to process like that much data, and how long it's going to take, and then how horrible that delay is in a control loop. Right? It can be really, really bad. Second thing, please, whatever it takes in terms of payment, but don't take away from us the benefit of laughing at your C code, because that's one of my great joys in life, is seeing how somebody else wrote something and go, oh wow, this is a whole new way to write bad unreadable code.
Yeah.
But the third thing about that is I have noticed that when other people look at my C code, they usually are thinking exactly the same thing. Even though I've been doing this for years and years and years and years, everybody else is like, hey, if you just wrote this, it would be so much better. But the thing is, the reason why I'm saying this, Chaz, is because I've learned to be so much better a programmer by like having a thick skin and having people tell me, your code is stupid. Why don't you do this way? Right. And, and I'll look at it like, wait, he doesn't know what he's talking. My code works. What? And then about a half an hour later, I'll be like, that is really a pretty cool idea. And then the next time I'm writing a program, it's like, oh yeah, I'm going to use that idea that Chaz gave me. It works really well.
Yeah. I just I'm out there to do. No, I hear you. Like that's why I'm willing to share it, because I don't care if something. I just want them to know that I'm not going to try to defend that it was the right way to do it. So
that's great. That's the right attitude.
Here and put in my shameless plug for code reviews now.
Yeah, for sure.
Oh, absolutely. Sure. It's the best way to go. Yeah.
It's amazing how many professional groups do not do code reviews. And no, it drives right to the same thing. Everybody's got a different way to do it, and different teams come up with different styles. And that's letting out one of my interview questions here, but that's one of the purposes of a code review, is to share and learn and teach other people. Just my shameless plug for professional software development and code reviews.
Yeah, I was talking with one of last week. I was in the field. I was in South Dakota, and I was talking to one of our developers, and he said something that just like scared me so much. Like, he's an embedded hardware designer, a developer. He writes software, just like firmware, like mono .NET applications in embedded systems, and he's just talking up ChatGPT so much. And he's like, it's so easy. You could just search for stuff. I'm like, please don't tell me you're writing our software in ChatGPT. Because I mean, I know it's great, and a lot of people have a lot of fun with it. And it is very interesting how it does its job. But like every time I use it, and I get that you can keep asking it questions, but I'm like, it's just stuff you could Google. That's all it turns out. And like, it's definitely not always a great way to do it. Like every time I go and have it, like, just for fun, like, write me a C software like for wall following, and it just churns out like the same. You guys have all, if you've ever done or looked at any wall following, it's like the same, like 2 different examples of how to wall follow, and it just couldn't churn out anything else. And so I'm like, I guess I got to do my own thing, because I don't want to do these 2 variants. I don't particularly care for them. So, but yeah, I'm worried that there's like our software developers are going to be they're just going to be going straight to ChatGPT and write all my code for me, and that's how Skynet starts. Just so you guys know, so gonna sneak in that Skynet code in.
I don't know if anybody else has tried it, but I have, and so far I'm really not impressed with the results. I will say that actually it kind of comes back to what you were saying, Lloyd, about code review, is that I've asked ChatGPT how to write code, and although the code that it wrote was horrific and couldn't possibly have worked, it was like having another developer around to kind of like spark an idea, and then I was able to take that and run with it. So it was still a positive interaction, even, and also I got that great joy of seeing how stupid its code was. So that's always fun.
So my takeaway on the ChatGPT thing, and just for reference, we did an open discussion. I hosted an open discussion here, I think it was 2 months ago, and I also did basically the same one at Northwest C++ users group, where we both times we got into asking ChatGPT to write code for us. Basically, what I've found is it can do it to a certain degree, but fundamentally, it cannot do anything beyond what you could just look up yourself. So if you go into GitHub or any of the open source code repositories and say, find me a coding example for blah, ChatGPT can regurgitate that to you as well, and sometimes with a few modifications, but it's not creating code by itself. And we did the one here, we had it doing a what was it? I think it was a line follower, and we asked it to modify the code a couple of times. And it was very obvious that, it could kind of sort of follow instructions, but had no real understanding of what it was doing.
Yeah,
I'm not worried about my day job yet.
so I remember it also made a bunch of errors.
Yep.
And if there's one thing I hate more than writing code, it's trying to fix somebody else's code that's broken.
Yeah. Now
Yeah,
that said, I have run across actual humans that write code the same way Chat GPT does, but that's another scary story.
Oh, yeah.
Yeah, the other one I saw online the other day, it just absolutely made me laugh so hard, was somebody pointed out that in order for ChatGPT to work, customers would have to accurately describe what they actually want in their product.
Yep.
And so the upshot is our jobs are safe.
No joke.
Let me put it this way. I'm in aerospace, and even in that domain, getting people to write proper requirements before you start writing things is a challenge. It's interesting to see you nodding your head, Steve. So it's not just the places I've been. And yeah, if you can't get the requirements right, you're not going to get the product right.
This is one reason why I think, I mean, I know that college students and degrees, there's already a stunning amount of information that people have to learn, but I really sort of feel like we should start requiring basic programming for all degrees. Like you want to get an English major, you want to go into especially management, you need to be able to write a simple program and debug it.
Yeah.
In
I'm stuck in that one.
In my line of business, the program owners, or the that's what they're called anyways, they own the software whatever suite or the component, and they've like taken the stance and actually changed over the last 2 years. And instead of having like they fight like, do not tell me how to do it, I do not care how you want it done, tell me what you're trying to. Oh yeah, my internet's bad, sorry.
That's okay.
Yep, drop the video. So instead of like telling them what to do, they want us to tell them what are you trying to accomplish, like what do you want done, instead of like telling them exactly how to do it. So just because the software developers themselves are better about deciding like how it can best be accomplished, it seems like they've given the power to the software developers to decide how it's actually accomplished now, instead of so it's kind of interesting, that shift in software development. Instead of like having to take, this is exactly what you're trying, instead of taking like how you want me to accomplish it, you let me accomplish however I want, and you just tell me what you're trying to get done.
It's interesting you mentioned that, Chaz, because the project I'm working on now, we actually have a very senior systems engineer that's coaching us on writing proper requirements. And as folks know, I've been around this for a long time, and I've never gotten properly coached on how to write requirements. And one of his, he's got a couple of rules that he really punches down on. A requirement describes exactly one thing, right? And the second one is the requirement tells you what needs to be done, not how to do it. And it's right to your point,
Yeah.
You need to do this. How you do it is up to you, but this is what you need to do. And it's when you get those two together, and I just said them, they're super simple, right?
Yeah, I actually
can a set of requirements actually gets a lot better.
So Fortune, Global 500 style, we're in the Global 500. The software that they're producing, when you give them the free rein to do what they want to do and not tell them how to do it, has been a lot better in the last 2 years that they're developing. So they've developed some like super innovative things that people just didn't think of, right? And so it's pretty awesome when you can unleash a software developer to like go at it their own way, if you will.
Yep.
One of the things I've kind of been getting more and more into, and and I don't know why, but I didn't like glom onto it early in my development life, but lately I've been enjoying it more and more. Is writing code to the test. In other words, you write the test first, and then you start writing code until it passes the test, right? And now I'm really starting to look at like how to write, because writing a good test is really hard. As a matter of fact, it's probably as hard in some cases, or harder even, than writing the code that passes the test. But I'm liking the idea of like having a good requirements doc, and then from the requirements doc writing a set of tests, and then from the set of tests writing the code. And that seems like a lot of extra work, but when you're working on a really big project and there's a lot going on, I think it really helps. I'm curious if you have any feedback or experience on that. I've always, just so you know, I've always worked on like small projects with very small groups. Almost everything I've done has been like right next to the electronics, like device driver, low level control type stuff. And as my career goes on, I'm finding myself working more and more and more on larger, more complicated systems, which are a combination of a lot of things. So I'm always looking for advice on how to work better in that way.
Yes. So what you're describing is, generally known as TDD, or test-driven development.
Mhm.
I've done a little bit of it, but what I've done is mostly in the R&D space. And the problem with doing TDD development in the R&D space is a lot of times you don't know actually what you're trying to do yet until you do it. But I think what you've discovered, if you've got a requirement, you codify the requirement to the test, and then you write the code against the test. Just intuitively, that sounds like a really, really good way to do it. I'm going to see if I can try that with a team at some point.
Also, it helps if you put a cutoff time in for when the customer can change their their project requirements, so that you don't have code or feature creep that happens constantly throughout the project.
Yep.
Now, well, that's another one that's like
down about that, but
yeah, I was about to say, like, I don't know how you do that. I mean, it would be so nice, but there always seems to be a sales department and a management department that overrides whatever I mean, I don't know. Hopefully they're taking it back to the customer and saying, after this date, you can make changes, but it's going to cost you more, right? As opposed to just, yeah.
Well, I was working in aerospace, and we had customers that were making code changes within months of release, and we couldn't build the items that fast. And it didn't matter if you charged them more money, they would pay it, but we were screwed. So it was, no, you had to have a project manager step forward and say, bullshit, we're not taking extra requirements. You didn't ask us this in the beginning, and we cannot do this at this point in time. And it was a big, very demanding company that was just getting into aerospace, and they thought they could just do anything at the last minute they wanted to, because that's how they did it in their other factories.
Yeah.
No. And it was not tenable in our environment. And we had to draw the line on them, because they were changing stuff within weeks of release, and it takes months to get parts built, not weeks.
Yeah.
Oh, yeah.
The same
Yeah.
thing.
Yeah. But,
but it's funny because people, that's like more intuitive when you're working with like physical objects, because of like lead times or whatever. But people have no respect for lead times in software development either. Right?
No.
Yeah. It's like really hard to get them to like be like, well, just change the code. Like, do you understand how long that's going to take me?
Yeah. Okay, folks, we've got about 8 minutes till the formal presentation here. So good discussion. I think what we'll do, if there's no objection, is switch over. We'll give people like a 10-minute break, and then we'll come back. We'll get Charlie set up, and we'll get on with the formal presentation. That work for folks? Okay, and I'm going to go ahead and get a timer set up here. And there's our 10-minute timer, and folks can keep chatting or whatever. I'll leave the video going, but yeah, we'll go with that.
That was pretty cool, watching Lloyd walk away into space.
Well, where do you think he's coming from, huh? I used to work for, I retired from Boeing a few years ago, and oh my gosh, I worked on a number of data system development projects, and holy mackerel, is that a nightmare of trying to figure out what should these things be able to do. And everybody wants a system that can record anything from DC to light to can record terabytes of data. You start trying to put all these requirements together and try to build a single system that can do it, and it's not possible. You can't make one system that can do everything. And yet, as you start multiplying the number of systems that you're doing, of course, that increases the cost, and it expands the size of the software, trying to, and then maybe you start going down a path and you realize that what you thought was going to work in terms of a solution, it won't, either because of hardware limitations, software limitations, speed, whatever it might be, something that just all of a sudden now you run into a dead end, you have to back up and take off in a new direction. And I'm just glad to be out of that.
Yeah, the guy that I work for now, one of the things I really have enjoyed is he has this very clear line that he draws between research and development and productization, if you will, and how R&D works better if you go bottom up, where you give the developers a lot of control and a lot of autonomy, and you understand that they're going to try crazy stuff and it's maybe going to work and it's maybe not, and you don't necessarily have a high rate of guaranteed success. Something may work or it just may not, and you just have to be open to that. And then on the product side, it's more like you're not trying to make big leaps forward. You are making big leaps forward in R&D, that's the point. But when it comes to productization, you're taking something where there's already kind of a proof of concept and you're making small changes which have a very high rate of success, which are more kind of directed by management and are kind of top down. So he draws this really clear line between R&D and productization, and that's something that has really helped. I really like it. I'm super impressed.
Mm-hmm.
Yeah, I like that approach. I've kind of worked in both spaces as well, and the R&D spaces, I've had cases where there was too much. They didn't take enough risk, and
right.
In the product cases, they occasionally try to make these wild leaps because they get themselves into a corner. Like, we need to do something big and dramatic at crazy high risk when you could be doing something simpler. Yeah,
it's that never happens to me, and I'm definitely not currently going through that right now.
And I believe you.
The other thing too is it's kind of interesting to me how sometimes it's really good to work in R&D because you get to do your own thing and really have a lot of autonomy and really there's good things about it. But sometimes you also get tired of all the failures, oh, that didn't work. Oh, that didn't work. And it's really nice to switch over and do something that's, hopefully simpler. That's how they sold it to me. That has a high rate of success. And then, anyway, I can't say much more than that. This isn't being recorded, is it?
Yes. I left the tape running. Sorry, folks.
It's all right. No worries.
Hey, Charlie, if you're on there, we can go ahead and start getting you set up as well.
Yeah, I'm on. I'm on.
Okay. You're pretty comfy with the screen sharing and all that?
Yeah, yeah.
Okay.
Yeah.
And I'm not going to worry about it. Yeah, on the requirements thing, I've got one guy that I work with. Actually, it's the same guy. He coined a lovely term because, you know, the group I'm working with is like, oh my gosh, we can't do waterfall, you know, and they're kind of doing this agile stuff in aerospace land, which, you know, works to a degree, but it's, you know, something in between would be kind of nice. So the other guy kind of coined this term I just love. He calls it water climb. So basically you build the product and then you work your way back up the waterfall to the requirements. Not the ideal way to do things.
You have a meeting where we just talk about all of the horror stories. All of
yeah, that would be. We should probably anonymize it so nobody gets in trouble with that one.
Exactly.
Everybody can come in anonymously. We'll get something to mask your voice, no video, and you all the horror stories that you've come across in your career.
I love it. I love it. We'll have that where they do that backlit thing. Everybody backlight your webcam so you can only see the outline.
That would actually work really well. I went to a talk one time and they did something like that where they had this was at a conference. It was years and years ago. I think it was actually Embedded Systems Conference when it was popular. So this is like 20 plus years ago. They actually had people stand up and describe, you know, a nasty, nasty bug they ran into. And they you know, basically they did it in a format where you stood up and said, you know, your first words were, I have bugs, and then continue down that whatever you were going to describe. And there was some interesting ones in there.
Was it Isaac Asimov wrote a series of stories that were they were fiction, supposedly. I'm trying to think of the name of the series, but it was about a set of doctors. Oh, it was the Black Widow Society, I think. And it was about a series of doctors that meet and talk about the patients that they've murdered. And not intentionally murder, but the point is that they have this sense of guilt about errors that they've made or things that have gone wrong, and then the patient died. And so it's a very closed, very anonymous kind of society where they only meet with, you know, amongst themselves. And then the idea is that they, you know, try to, you know, feel some sense of compassion for each other and then for themselves, because they've all made these mistakes. And I think the last book or the last story in the series, the society, I think, breaks up because some guy brings in a case where he hasn't yet killed the patient, but he pretends that he has in order to get feedback from the other doctors about what he could have done that would have, you know, saved the patient. And then he goes and tries to save the patient with that data. And then they're like, no, you can't do that. And they all quit.
So we got just a couple of seconds left, but I'll share this one. There was actually, you know, we need a little more of that in some of the aerospace stuff too, and the mission critical software. So one of the books I read on was on DO 178, had a line that just absolutely stuck with me. You know, basically, you know, from the first part of the book and talking about the need for this. And the guy who was making the quote. The guy who was making the quote was basically saying, you know, in the case where there's negligence, right? Or, you know, somebody did something and people died as a result, you know, airplane crash, product exploded, you know, something like that. He made the case, or he made the point that, you know, they can usually get the person off from a legal standpoint but it usually doesn't matter because in a real world sense, by that point, the engineer is so guilty they've actually committed suicide. And I thought that was a really profound statement to be making it, you know, at the high at the mission critical level. And you know, so it's like, yeah, you know, there's some real world cost to getting this stuff wrong. Any case, on that lovely note, Charlie, let's go ahead and get you set up and presenting here.
Sounds good.
Let's see. So if you want to go ahead and share a screen. Yep, I'm going to go ahead and actually, I don't think I need to do anything for that. I think it'll just work.
Hey, cool. You guys all see the screen?
Yep, looks good to me. Anybody not seeing the screen?
Cool,
Okay.
awesome.
Go for
it. First off, I want to thank you guys for inviting me to speak to you all. And second of all, I want to thank you guys. I've noticed on your website, you guys do a lot of outreach, you know, sort of like, especially with First Robotics, and, you know, those programs like that have been impactful in my life. Without it, I probably wouldn't be doing robotics today. So here's a picture of me way back in 2014 at the championships in St. Louis. So yeah, so thank you all for all the outreach work you do and for inviting me over to speak. Overview of today's talk. We're going to talk, talking divided into two sections. The first section is we're going to talk a little bit about the lab I come from, which is the Hawks lab, and the work we do there. And then we're going to talk about the world's highest jumping robot, which is what you guys invited me for. So overview. So what is the Hawks lab? So Hawks lab is directed by Professor Elliot Hawks. And we're at a lab in the Department of Mechanical Engineering at the University of California, Santa Barbara. So our research focuses on developing innovative design concepts and applying non-traditional materials to solve challenging problems in robotics, medicine, and biomechanics. So what do we work on?
Charlie, your audio is getting a little choppy also. Maybe move a little closer to the mic and or maybe turn off your video. Sorry.
Oh, sorry about that.
Nope, that's way better. There you go.
All right. Yeah, so what do we work on? Hold on. What do we work on? Well, you can't really talk about our lab without talking about bind robots. So it's a major thrust of what we work on. And we also work on a whole bunch of other different types of things. They don't really all fall into one category. And then we also work on jumping robots as well. So a whole bunch of stuff going on. So what are Vine robots? So really the development of Vine robots started with the question is how do we reach faraway targets over challenging terrain, right? So the obvious solution to do that is to develop some type of rover-like mechanism or a moving robot. So you have the Curiosity rovers and stuff like that, and also like the Boston Dynamics Spot Dog robot. And those robots are complex, right? To handle all the challenging terrain, you need to have a robust locomotion mechanism to get over it, and your robot needs to be robust enough to handle that terrain. But there's other things that navigate challenging environments, right? Like what about stationary objects, like things that we think are traditionally stationary, right? So in biology we have like cells, right? And we and cells and plants, right? And they get to navigate their environments by growing towards them, right? So for example, like a nerve cell to reach to grow to a new area, they grow through the tip, and they can navigate through all these cells. And then in a plant world, you can think about these like pollen tubes, right, to reach the the egg of the plant. These tube organelles that grow towards it, allowing this the sperm to reach the egg. So how do we implement growth in our lab? right? So we have basically an inverted tube. So you can think of like a sock. When you roll a sock in and out, you get this nice sliding motion that allows you to grow towards a target on to robustly, to grow. So what are the advantages of a design like this? Well, one, you're growing from the tip, right? So you can, and you're really not sliding the whole body. So if you think about it, like if you're sliding something against like a whole bunch of rocks, you're gonna get a whole bunch of tears, right? So if the object is stationary relative to the environment, you're not gonna get all that drag from the environment, and you're not gonna get caught up with all the detritus on the ground or in your environment. So so that enhances mobility quite a bit. And secondly, you can get huge length changes, right? You can grow these things to tens and tens of meters. And you can also, control these because they're quite soft. You can easily control the direction of the motion of these robots by simply changing the strain on each side. So here's some demos of these robots in action, right? So you got these robots steering towards all sorts of different targets, and how they steer is they have these pneumatic-based muscles on the side, and these pneumatic muscles, how they work is they're basically a simple pouch, and then when you inflate these pouches, they contract in length because their volume increases, and that leads to contraction. And by straining and shortening one side, you turn towards that side. Did that make sense to you all? Okay.
I've got a question. Are you contracting the entire length, or do you have some way to control at which point along the device you're doing this contracting?
That's a great question. So I'm not too sure about this example, but you are controlling individual segments. So usually you would control a length of the robot. So it can either be the whole robot, or if you put a lot of different tubes in, you can control more segments of it.
So basically you have to run like tubing up there so that you have regions.
Yeah, yes.
So in this bottom right example, it's definitely making two turns.
Yeah. So so there will be at least two sections of tubings, right? So for that to occur.
Cool.
Yeah, and then that's actually a fantastic question because it goes on to the next slide. And you can also, instead of running pneumatic tubing to all these actuators, you can also use an environment to steer. So you can also steer these robots with heat. So basically, to do that, we have basically the same muscles as in the previous slide, but each of these muscles are individually sealed, and they contain a bit of low boiling point fluid. And when these low boiling point fluid evaporates, they expand, and again leads to that contraction and allows it to steer towards a heat source, right? And this is something I worked on actually fairly recently. So here's a nice video of, hold on, sorry about that. Yeah, so here's a nice video of these robots responding to a localized heat source. So you can see how each of these individual pouches have different amounts of heating, and it leads to slightly different amounts of curvature of the robot. And then, here's some demos of the robot steering towards like a heater and stuff. Heaters. Yeah, so this is some work I worked on over the last year, and it was just it's some fairly recent work. Okay, so what are some applications for these robots, right? So one application, is like when you think about these, it kind of reminds you of roots, right? So, and there's tons of naturally you want to explore stuff underground, right? And turns out there's a lot of interesting stuff under the ground. in places like Mars and icy moons, around the gas giants. So there's all sorts of interesting stuff that geologists are fascinated about. So how do we go underground, right? So one is we can look towards biology, right? And the way how biology burrows underground is they control the ground reaction force, and they do it. The reaction forces in the soil, and they do it with 3 different mechanisms, right? You have tip extension. So if you think about roots, in order to go through all that soil, if you slide a root through the ground, it's going to take a huge amount of force as they grow through it. And then if you look towards animals like the octopus and some type of clams, they do fluidization. So they change by blasting a jet of water to the sand. They change how they can change the adhesive forces that the soil has. And then with animals like this, what is it called? The sandfish. Yeah, sandfish. They have, their body is asymmetric, so that they can control the ground buoyancy force of the sand around them. So how we do this with vine robots, right? So basically, to do this, we have the 3 principles done. So we have tip extension with the vine robots naturally give you the tip extension. So because you're going from the tip, you're not sliding through the sand. And we also have this wedge thing that gives you a little bit of asymmetry, so you stay underground. And then tip fluidization, right? For fluidization, so you can control how viscous, how much drag the sand gives you around you. And then related to that, we also have the bit of directed flow. So what's interesting is you notice, actually, one interesting thing to do is to stay underground. We actually have to point the jet of air downwards rather than upwards. And the reason you do that is because in sand, in granular media, the buoyancy force is a little different than what happens in water. The buoyancy force comes from the difference in the lithostatic force, lithostatic pressure, and then by fluidizing the ground below you, you decrease, you free up the sand, and that reduces the pressure, not pressure, it reduces the force required to penetrate downward, and that keeps your body, it prevents the sand below you from pushing your body up. So that keeps you below ground. So here's a demo of the robot navigating through an obstacle course in the sand. I should have highlighted the obstacles, but there is a whole bunch of. Actually, hold on. Yeah, sorry. This is going through a bunch of sand, and yeah, so successfully travel through that, through growing, and then here's where it's fluidized. You can see the the sand going all over the place. So we're currently investigating. How to use these, more for for future exploration missions on the moon or Mars, and hopefully we'll hopefully do some 0G tests. So one of my colleagues is working on that. Another thing we're working on related to growing is we're trying to put ground anchors into the soil. For example, you might want to put a seismometer underground or a temperature probe, and we're trying to figure out how to get burrow deeper. And we're looking at stuff like adding root-like structures, hair-like structures to these vine robots, so we can get a little bit better anchoring into the ground. So the next applications we want to think about are medicine, medical applications, right? So there's a lot of, if you think about the body, there's a lot of really challenging places to get to, right? So one, an obvious place is, your stomach, right? When we do a colonoscopy, you have to go through the colon, and that's a pretty challenging environment to navigate. So those are, potential extensions to it, and also different vascular structures in your body So we got a whole bunch of different collaborations of a couple of different medical institutes working on developing Vine robots for medical devices. But the real big focus right now in our lab is intubation. So, trying to get airway management for when we can't breathe and you need force oxygen into your stomach system. So here's an old prototype of a device that can navigate through this throat and get air into your lungs. So this is an early prototype, and I can tell you, well, I don't know how much I can tell you, but the prototypes are much more advanced now, and we have done some cadaver testing. So hopefully in the next couple of years, we'll see a Vine robot like intubation device out there in the market. And hopefully, none of you guys will actually have to use it or get used on, but in the next couple of years, hopefully we'll have something out there. So there's also, there's a ton of Vine related stuff we've done. You can find more about them in this nice Veritasium video that we have. There's a nice Veritasium video going over what we've done as well. So, all right, so other stuff we've done. So here's example of a photothermal powered soft robot. In quotation marks soft, but so trying to figure out how we can harness the natural the world around us to power these robots. So here's a robot that's flipped with a pouch motor with phase change fluid, and it's flipping over based on this input. So we're trying to figure out how to design these soft robots to operate in the world around us. The other things we have is controlling. We're working on controlling soft robots. So the challenging thing about soft robots is they're technically they have almost infinite degrees of freedom because they're continuum systems. So they're challenging to model, and then the manufacturing process for these robots are they're very artisanal, I guess, one way to describe it. So there's a lot of variation between these soft robots, and they're hard to model to get all the modeling correct. So we're looking at using something like the Koopman operator, using Koopman operator theory to do model predictive control for these robots. I think I'm not too familiar with the Koopman theory, but from what I understand, it's similar to it's a common filtering method. So we got some nice results of controlling these soft robotic arms really fast. So I think hopefully we'll have a paper out soon in the next couple of months. So be on the lookout for that. And then we have the untethered isoperimetric soft robot. So this giant robot, and basically how it works is there's a whole bunch of there's a fixed tubes, and by changing the position of these nodes right here, you can change the shape of the robot, and that allows you to roll around the world and to navigate the world. So we're working on that a little bit right now, and then we're also working on this glider so that can jump in air. And basically how it works is we have these movable flaps, and these flaps when they're in flight, they're flush against the wing, and so they don't impart a whole bunch of so they're flush against the wing. But when you want to jump up, so when you start jumping upwards, when an object collides against the wing, basically it forces the wing upward, and that creates an airflow that forces these flaps down and allowing it to go up. So there's a bit of asymmetry in the drag, and that allows you to jump over these small jumps mid-air. And the reason we're looking at this is with drones are in comparison with drones, drones are very good at being very agile. But the problem with drones, like the quadcopter type drones, is they're very energy intensive. So, you know, can we get something that's as efficient as a glider or a fixed wing aircraft, and then but can also be just as agile? And so we're trying to look and see if we can jump, do some like a jumping motion in midair to get the best of both worlds. Okay, so with that, we can go to the next topic, which is the world's highest, talking about the world's highest jumping robot. So, yeah. So before we start, you know, there's quite a bit of a team that was involved in this project. You know, from quite a lot of people from Disney and a couple people from Caltech as well. And thanks to the whole team effort, we were able to get onto the cover of Nature. So, you know, we built this cool dinosaur looking robot to do it. No, I'm just kidding. But it's actually, we were, they just mentioned us in the cover, in the bottom, in the bottom text. So the history of jumping robots. So basically, as far as we can know, is the development of jumping robots really started over about 50 years ago. And there wasn't even a robot first. It was more of a concept of how to navigate around the moon. So this guy named Seifert at Stanford, he proposed using these jumping, these jumping pogo sticks. These pogo sticks to navigate to move astronauts on the moon. And that's yeah. And then since then, you know, there's that's inspired a whole bunch of researchers to look at building these jumping mechanisms and jumping robots for all sorts of applications. But most of these applications have really been focused on bio-inspired jumping robots. I mean, you look around in the natural world, you know, think of kangaroos, frogs, and, you know, grasshoppers. They're all really good at jumping. And a lot of the people have been, you know, trying to base their designs on trying to be as bio-inspired as possible. And, you know, and naturally that lends itself to a lot of people creating a whole bunch of models of biological jumpers. And models are pretty complete out there. But there's really, a lot of people haven't been really thinking about, like, really what is the difference between, you know, biology and engineered systems, right? So, like, we're fundamentally just different. You know, we've created things that are just fundamentally different than what is out there in biology, so we can have different capabilities. So that leads to the two questions that we have in this project. One is, how do the energy production limits differ from biological and engineering systems? Like, yeah, fundamentally, yes. And then second, based off these differences, how should we design a jumper based off our capabilities, and how do we maximize our jump heights? Yeah, and the images right here is one is a tree hopper, which is one of the best jumping insects out there, and here's an image of one of the robots that we built. So in this part, where you know, the talk is going to be divided into 3 parts. First is we're going to talk about the production, like the fundamental differences between biological engineered jumpers. Then we're going to talk about the design of these jumpers, and then we're going to show some cool videos of those jumpers in action. So, okay, first question. So what is the difference, right? So let's first begin at the big picture. It's like, what is the model that we use for understanding this problem? So basically, jumping can be divided into 3 phases, right? So one is the stretch phase, which is like where you load up your legs and stuff, load up your legs and springs. Second is the actual jumping part, where you are, you're jumping and then you're in flight. So, okay, so then there's 2 ways typically there's 2 ways of achieving a jump. One is a direct drive type system, where the motor directly drives the linkage, and how to jump. It's basically how you jump, right? You know, I mean, technically there's a bit of tendons, but mostly you're using your leg muscles to drive the jump. And then the other type that's common is a spring-based design. So you use a motor or a muscle to store up energy in a spring, and then when it's come time to jump, you release the spring and you go off. And that's the type of jumper that we use for our system. And then there's different motor types, right? So there is the biological motor, which can only do one stroke, and then the engineering jumper, which we have, there are rotary motors and stuff. So basically, the big difference between biological and engineering systems is biological motors can only do one stroke, right? So you can, once you contract your muscle once, you really can't contract it anymore. But if you think about the rotary motor, you can keep on spinning that motor almost like basically for infinite time and keep on doing work, right? You're only really limited by their energy supply and the capability, the wear of the motor. So this leads to this concept what we call a work multiplication, just because by the fact that you can spin a motor over and over again, you can store you can produce incredible amounts of work, and basically that drives the fundamental difference between biological jumpers and engineered ones. So basically, biological jumpers are limited primarily by their motors. They can only do so much work, but with an engineered system, you can do the upper bound is almost infinite, right? So so basically that means the jump capabilities of these motors of these systems for engineered systems are just limited by how much energy you can store into a spring, and for biology is how much energy just by the motor, just how much energy you can put into the spring. Okay, so then we're going to talk about the models a bit, an overview of these models. So okay, because you can only store energy so much, you can't really store more than about 200 joules of energy into the muscles. You can't really produce more than 200 joules per gram for biological systems. So the shorter your so eventually you just saturate out. Even if you allow your muscles to run for a long time, you just can't produce more than 200 joules per kilogram. But with engineering systems, you can just basically go on forever. But if you weren't limited by linkages, the linkage mechanism, by adding linkage mechanisms, you can't. You really don't get the energy density does not go on forever though. Okay, so basically, okay, so then for how does this affect the system if you use a spring? So what a spring does is it allows you to store energy, right? So basically, if you're a small scale object, you can't, your legs are short, so your jump time is going to be very short. So if you want to jump very high, you want to be able to store that energy into a spring, right? So the spring allows you to decouple a bit from the power, the duration of the motor. So for biological systems, because you can only produce about 200 joules per kilogram, you really can't store that much energy into a spring system. So at most you can store about your spring mass is only about 0.025 like 2.5% of your motor mass. So you really can't store that much energy. But with an engineered system, because you can produce work for a long time, you can store, you can almost reach the theoretical limits of materials, right? So the theoretical max limit of these springs is about 8,000 joules per kilogram, and in actuality, structure and stuff like the structure of the spring gets down to about 2,000 joules. So you can really put enough energy. You can use a really small motor and you can still store almost 2,000 joules per kilogram into these springs, and that and really enables you to jump incredibly high heights. So basically, what are these insights? What does that lead to? So for biological systems, you should still use springs if your scale is below 1 meter. But once you get bigger than that, you should use muscles, right? So basically, if you think about it, like if you think about locusts, they're spring-based. They're spring-based jumpers. But once you get to larger scales, like human-scaled dogs, and kangaroo, I don't know. Well, like humans, we're really jumping with our muscles. It's just because we just can't store, and that's because we just can't store a lot of energy into the springs. But for engineered systems, it's because of this work multiplication, we can use springs into incredibly large scales, up to about 100 meter. If you build robots up to about 100 meter scales will benefit from using a spring-based system rather than a direct drive system. And then once you get over that, then a motor-based system would be more advantageous.
I have a question.
Yes.
This length you're talking about, is that the length of the robot or the length of the jump?
Great question. That is the length of like the robot, essentially leg length.
Okay.
Yeah. So for so basically, like unless you're building a 200 meter robot, you're gonna be using springs to jump, right? That's kind of a little crazy to think about. Okay. So sorry. Okay. So for data insights, for biological systems, you really only can get about the spring to mass ratio about 0.025, pretty small. But for engineered systems, what this tells us is your spring that you use on your robot needs to be as big as possible. So for our robot, we have basically a factor of, about 1-to-1. It turns out actually, if you get bigger than that, you don't really get jumped that much higher. But we have about 1-to-1 spring mass to motor ratio. So yeah, so basically, so basically how you can improve your jump heights, right? So for biological systems, the more energy you can produce from your motors, the better you're going to jump. The more energy you can put into these springs, the higher you will jump. So having better muscles will increase your jump capabilities. But you notice here, you don't see the engineering mechanism limit. That's because you have this work multiplication effect. You can keep on producing work. So there's really no concept of specific work for engineered systems, because you can keep on running that motor forever. And then again, because you're storing energy into a spring, it doesn't really matter how powerful your motor is, right? You can always the amount of energy you store, you can always gear down your system and you'll store more energy. But really, the big effect is here is like how you can jump higher. For engineering systems, you want to have as much high specific energy as possible. So the better spring you have, the better you're going to jump for engineered systems. But because in biology, your muscles are only so good, right? They only can produce about 200 joules per kilogram. They really, having a better spring doesn't really make you jump higher. It actually doesn't affect you at all, right? You just can't produce enough work to take advantage of the better springs. So how do we actually use these insights to build a jumper? Well, so naturally we chose, we maximize our spring mass to motor mass ratio. So, and to drive such a big spring, we had to use a really small motor. So our motors were geared down to 1,000 to 1, and most of our jumper was basically a giant spring. So what does it look like? It's not really much of a robot in a traditional sense. It's basically mostly spring right here. So we have this carbon fiber segments, which form our springs, and then these rubber bands, which I'll go into a little bit later. And then the construction is actually fairly simple. I mean, we got these Pololu motor from one of these Pololu motors, and a fairly simple latch system, and all these hinges were actually made from fabric, and there was quite a bit of super glue holding this all together. You could probably build one of these in your garage. They're not. I mean, it takes some finessing to build, but they're not. But they don't really require that much special equipment to build. So here's the detail of. Sorry, go on.
Just on that last slide, give us a sense of the size of what we were looking at there, like those spring segments. How long are those?
So these are about 30 to about a foot long.
Yeah. Oh, yeah. Okay. Pretty short then. Okay, 12 inches, and then there's 4 of them. Okay.
Yeah.
Okay.
So it's about it's about a little over. I mean, in total it's a little over a foot, but these spring segments are about a foot. All right.
Those are tiny motors then.
Yes. These are the tiny, like Pololu. Like, have you seen these Pololu motors before?
I'm not familiar with them. That motor, just looking at it, I would guess it's like the motor itself is 1 inch long and the gearbox is 1 inch long. Is that about right? Or is
hold on.
Seeing that's a foot, that makes it's even smaller than that.
So actually the total I would say the total motor is about 1.25 inches, including the gearbox. So these motors are not even 1 inch long. They're a little shorter, about 3/4 of an inch. I would say about 3/4 of an inch long.
Wow.
So those are they're super cool. I mean, you can just go on Pololu, and they're like $6 a piece, and you can get them geared down. They come in a whole bunch of gear ranges. So the ones we use is 1000-to-1, and they come in different versions, like high and low powered versions. But they're $6, and they're super. Yeah, they're incredible.
So yeah, I'm guessing that you're going to use a string that's wound on a spool. Where is the spool in this drawing?
Yeah, so actually, hold on, let me go to the next slide. So the spool is actually the motor shaft.
Oh
so
my.
Yeah, so we're winding the string on the motor shaft, right? And that way we increase our mechanical advantage of the system, right? So if we had an actual spool, then the 1000-to-1 might not work for the system. And then the release mechanism is pretty simple. There's just a wedge on the string, and then once the wedge goes past the latch, it releases the swing arm, and that pull, and I guess that drops the string off the shaft and allowing the robot to jump. So it's a fairly simple part, simple design. So then the next thing we have is a spring that has an incredibly high energy density. We have energy density of about 2,000, almost 2,000 joules per kilogram. So you noticed, going back a couple slides, you notice these rubber bands. So what do these rubber bands do, right? So for these springs, you can imagine like a carbon fiber bow, and then there's the rubber bands are tied across the carbon fiber bow. So what that does is it reduces the peak stress of the carbon, like that's seen in the carbon fiber bow. So that allows you to get compressed even further than you would normally can to get more energy out there that way. And the other cool thing is it allows you to store some energy in rubber bands, allowing you to get a little bit more energy out there, right? So if you had a straight bowstring, you get this purple like curve, and then if you had a spring that's has rigid linkages and just the rubber bands, you get this green shaped curve. But then when you combine the two, you get this flat shaped profile, and that allows you to store incredible amounts of energy into the system. So what's a cool fact about these rubber bands is rubber bands actually has one of the highest specific energies out there. It's one of the best spring materials in the roll. I think it stores about it's either I think it's about 8,000 or 2,000 joules per kilogram. And the reason it stores so much energy is because even though it takes a little bit of force to stretch it, you can stretch it for huge distances. So that'll get large strains, so that allows you to store a large amount of energy. So yeah, so if you want to jump high, use carbon fiber and rubber bands. So that's a little bit, that's a little bit of insight there. So yeah, so here's the final, here's one of the jumpers we have. Again, the rubber bands, it's a hybrid spring with the carbon fiber bows and rubber bands storing, giving you a little bit of extra energy storage, and then they all connect towards that pivot. Sorry, the release mechanism. Sorry, the wedge right here that releases the latch.
So that picture we're seeing this. So how tall is that from the base it's sitting on up to the top of the little cone there? Is that
I would say about 6 inches.
6 inches? Okay, so it's pretty small. Okay.
Yeah, so these are small robots. They weigh about like 30 grams. So.
And does that string doesn't actually connect in the center there, right? It just slides by?
Sorry, what do you mean it doesn't connect in the center? Yeah, it just slides by, yeah.
Slides by. Is there an actual like tube or something like that to allow the string to slide? Or are you just
Yes, there's a tube, yes.
And that probably also gives you a little bit of stability as you're reeling it in.
Not really. I mean, it doesn't really. It definitely adds a little bit of stability, but I mean, this thing. Really, what's stabilizing it is just a different. The springs, like it's stable without the tubes. The springs, like just having a slightly different compression. I mean, it's naturally. It's mostly stable. It's inherently stable. So
It's just all the counterbalance forces.
yeah, they're all counterbalance forces.
Are the rubber bands look like are they tied from the center pivot to the edges, or do they go from one edge to the other edge and they just happen to go by the center?
They are tied to the center pivot.
Ah.
Yeah. Yeah, so then here's some videos. Here's a slow-mo of it taking off.
Whoa.
Yeah. Yeah, so it's quite a violent takeoff process. I mean, like in that last video, you notice how the rods slam into the center. That's actually one of the sources of failure for these is they do fracture after repeated jumps from that slamming motion. And yeah, you get about 300 G's of acceleration, which is just
Wow.
Which is incredible, right? So I mean, you're going from 0 to 28 meters per second in 9 milliseconds. So it's an incredible acceleration.
Can you go back to the initial configuration? How far down does it compress?
Sorry, let me. This one. How far does it come?
So it never goes more than that. That's the minimum compression we're seeing. It's basically, well, it's still elliptical, but it's not much farther than round. You don't get down to flat at all.
Yeah, you don't get down to flat. I mean, by the time you do that, you're just breaking the rods. So, oh, sorry, I'm just clicking by accident. You're always like that semi like pumpkin. You're pumpkin shaped. And then here's a picture. Yeah, so here's a video of it jumping over 30 meters, over 100 feet. You really can't see anything. It goes by so fast, but and then it ends with. Hold on. Yeah, so here's it highlighted. These black lines superimposed onto the image, highlighting where the robot is. So the robot's a lot skinnier and thinner. A lot skinnier and shorter than what's highlighted here, but yeah, we can get these things to jump about 100 feet. or more than 100 feet actually. So
Would you say that the ratio of mass of the mechanism to the spring is such that it likes to stay pointed toward the nose cone? In other words, are you doing the thing that you do with a skyrocket that keeps it pointed in the right direction?
I don't quite understand the question. So like,
So
can you
a
repeat that again?
skyrocket has most of its mass at the engine, and then it
Yep.
has a long stick that's there to kind of direct it so that it'll always be, the force will go in the desired direction of motion. And that's, I think, what this is doing too. Most of your mass is at the nose where the motor and the batteries are.
Mm-hmm.
And so as a result, it tends to fly such that the nose cone is pointed in the direction you're going.
Yeah, so to answer that question, it is, I don't know, it's definitely not super intentional for the, like this. I mean, yeah, I guess like it's
In other words, it doesn't tumble.
Yes, I understand. So it's top heavy for two reasons. One is it turns out actually the distribution of mass is very important. So the more mass you have above the spring, the higher you're going to jump, because your average center of mass kinetic energy is higher. So that's why we're top heavy, and that's just a nice consequence. The stability is a consequence of that design choice. So we didn't really design it for stability reasons, but for like because of average center of mass velocity reasons, it is top heavy, and that gives you stability. Does that answer your question?
Yeah.
Yeah. And then self-righting concepts. So you can also get self-righting by having these extra bows, these split bows. So there's the green bow is actually two parts, right? So there's one part that is not connected to the rest of the bow. So when it starts bending, it splits off, and then you get this a little foot kicking down to the ground, and that pushes you back up. So yeah, here's the robot self-righting indoors. And then, that self-righting allows you to jump like by itself over and over again.
How much do you think you could scale that up before the strength of the materials involved put a limit on it?
Ooh,
and of course the acceleration forces put a limit on it.
Maybe. Wait, I'm not quite sure about how much of the acceleration forces, but for static cases, I think these can go up to like a couple tens of meters in scale, and so you can go quite a bit bigger. Yeah, you can go a lot bigger, but you're not going to really jump much higher. Well, actually,
that was the next question.
But you won't. You will jump higher, but it's not significantly more.
So this design wouldn't get you to jump a mile or anything.
No, but if you put it on the moon, you might.
Is there some kind of a controller on this thing, or how does it, like it was laying on its side, and then the motor was obviously contracting to right the thing. How is it doing that? Just sort of an automated sequence or something?
So okay, these are incredibly dumb robots.
Okay.
They're not. It's basically there's not even any logic going on. It's just basically once it's connected to a motor, it would go. But yeah, we're working on making these more actual, like more robot-like by having controllers on it, and so it can be more autonomous. But right now, for these demonstrations, they're pretty dumb.
So what is the mechanism that causes it to release? It's basically when it's reeled all the way in is when it releases, right?
Yes. So these designs do not have controllable. You can't adjust how much the takeoffs on these.
Right. So you've got something on the string that like flips something and lets it go, right?
Yes.
That's what you were showing us in a previous image where you had like 4 images, and I didn't quite catch that there. So there's something that there's a little gadget on the string that hits something.
Yep.
Yeah.
Yes. So basically how this latch works is
Yes.
so you have, so this basically when you're loading the system up, the strings, the tension of the string is wanted to pull this pivot out of the way, right? The pivot is holding the string on the shaft, and because of the tension, the pivot wants to swing down. But then there's this small latch mechanism right here on the left that prevents that from being pulled out. And then once a wedge hits that latch, it frees the arm out, and then the string unwinds from the shaft.
So you can see it in the center image there. The purple opens the black part and allows the green part to be pushed by the orange spring. And that green part was the roller that was causing the string to be wound around the shaft. And then when that gets pushed out of the way, the string actually pulls off the end of the shaft. It unwinds, which is very efficient for getting that off. It looks like it stays connected at the end. Yeah. But yeah, that's very cool.
Yeah. The springs there's more of like to yeah, I mean, the spring also helps restore it to the original the door to the original position once the string's off.
So this current setup, you could only do one jump. You'd need something to reset it by hand.
No, well, actually, the self-riding concept, this design, because the spring restores it to the upright position, it can reset itself.
But what about the green lever there would have to be reset to be latched onto the latch?
The spring allows for that.
Ooh.
Yeah. So
what's actually, so the purple string, that's what pulls the green part down, but the spring pulls it back afterwards.
Yes, because it is so much tension. Yeah, the string is pulling the arm downward, and the latch prevents that from happening, right? Because the string's under tension. But then
the string that pulls the green part down.
Yes, the string is pulling down. Yes.
And then the orange spring brings the green part back up.
Yes. Yes,
cool.
That's correct. Yeah. So this is indoors. It's indoors. And then here's it outside.
Onboard cameras.
Yeah. Oh wait. Sorry, I'm just 1 second. Sorry. All right, self-riding outdoors. So here's the jumper, and then it'll jump over there. And then it can start winding itself up because of that spring, right? That allows it to reset, and then it's about to jump. Then it jumps again.
So are you actually able to control the angle? So in that example, it's actually angled inward towards the cliff. So does your self-riding mechanism allow you to adjust one side versus the other so that you can get the angle you want for your trajectory?
Yeah, you can tune that. Yeah, you can tune that mechanism so you can get the correct angle
Cool.
that you want it to jump at.
So it just keeps jumping over and over. How many jumps have you done in a row?
Ooh, that's a good question. I think it's 10 or so. We've done about 10 or so jumps. Yeah, these, yeah.
What's the amount of terrain you've been able to cover?
It's a good question. I mean, it was just like example right here. It's about, you know, about 30 yards. I mean, not 30 yards, sorry, 30 feet.
With this very simple mechanism, it's going to be a random walk, right?
Yes. And we, in future work, we're trying to make it more controllable. So we're trying to control the direction we're going to. But for this, it's just, it was more of a, you know, proof of concept, and it was very simple. And to jump very high, you really can't have that much extraneous. You can't really have that much mechanisms on it, otherwise you're not going to jump as high. But we are currently working on improving these jumping robots so that it doesn't do a random walk. Yeah, and then here's a video of an onboard camera. So these are like we use one of these drone cameras, and then it can jump. Yeah, and then you get a nice aerial view of the ground, and it flies and tumbling towards the ground. Well, actually getting caught, but okay. And then here's a video of it flying by. This is actually our building, and there's another video of it jumping and flying by. Yep. And here's a cool video of it jumping off a table.
And it's strong enough that you haven't had much in the way of having to put it back together after it's landed.
Yeah, and that's because it's very light, right? So a lot of these jumpers are in the order of 30 grams. So the drag force on just the aerodynamic drag on falling doesn't give it enough of a terminal velocity to be significantly damaging.
Do you use a compliant nose cone?
No, we do not. It's basically a rocket engine nose cone. So, and it doesn't really land with that much, too significant of a speed to really damage the robot. Okay, so what's next, right? So, you know, if you can jump 100 feet on Earth, you know, you can probably jump 600 feet on the moon, right? So we're really trying to see how we can take these to the next step. How do we bring these things to make these practical for space applications? So currently, we got a senior design team working on it. So here's the team right here. They're talking to some people at NASA about their work, and then their work is mostly focused on attitude control, like how do you actually steer, how do you control the direction that the robot points at when it's in space. So right now, so right now it's like in space, you have no aerodynamic forces to stabilize your robot. So if you have any off-axis torques applied during takeoff, you're going to be tumbling. So we need to figure out how to do that. So most of the work has been focused on like the simulation of doing work on a simulation. Another thing that students are focused on is steering, is like how do you point the robot before you jump, and finally how to capture the energy on landing. So because there's no air resistance on the moon, when you fall from 100 feet or 600 feet on the moon, it's a lot of energy, so it's going to be damaging. But you also, because there's no air resistance, you can possibly potentially capture it and extend the range of travel. And then there's also some questions about of how to improve the springs, how to jump even higher with the materials we have. So currently for the steering mechanism, we have a tripod-like design. Basically, you have different legs if your legs, and you just adjust the angle of the legs, and that gets you the steering mechanism. Allows you to point dirt to different directions. But we're looking towards moving away from this idea because the ground can be, if you have sand on the ground, it's not that easy to move the legs. So we're trying to move towards actually design more similar to the self-riding design, where you can steer within the robot, adjust the angle within the robot, and then jump. So that's what we're moving more towards. And secondly, landing. So it turns out, how do you capture? So then the next question is, how do you capture the energy upon landing with the springs, right? So it turns, to increase the range of the robot. So it turns out you can't really jump with these straight, the legs in the straight configuration, because it turns out the spring compression really affects how much energy you can capture on landing. So here we got we did some drop tests with these springs onto concrete to see what and to measure how much energy we can capture. So in configuration A, the springs, the legs are more or less straight, and then you can see upon landing they get this high, you get this buckling effect, you get this dynamic buckling. And that really limits the amount of energy you can store, because you're putting a lot of this energy into high modes of buckling, and you just don't have as good energy conversion. And then it turns out the more you have the spring, the more you compress the springs, so the rounder they are, it turns out the more energy you can capture from that. So this dynamic buckling effect is also what allows you to staple, for staplers to work, right? If you ever noticed when you're stapling a stack of papers, if you go really slowly, you're not going to be able to get that staple through, because the staple buckles. But if you hit the staple fast, it goes right through, because the staple can't buckle. The buckling force is dependent on the speed. So the higher the speed is, the more force it takes to buckle. So in order to maximize the amount of energy stored, we do not want high order buckling like we see in A. We want something more. We want to have lower order. We want something more like D, where the springs are pre-compressed, and you can get up to about almost 90% energy recovery efficiency, and that is measured by the fraction of energy stored versus the kinetic energy right before impact.
Are you reeling in the string as it's in flight in order to get that shape in D, or are you not letting it decompress any further than that so it holds that shape?
So we haven't really implemented this in a jumper yet, but how we imagine it is, yes, it would be more like you don't allow the spring to go straight. And it turns out the jumper actually jumps before the legs are fully straight. And that's because of because of inertial effects. So yeah, so having a robot already in configuration D, limited to at takeoff, won't really affect your jump height. But it will really allow you to have significant energy storage, or enhances its energy storage capabilities.
That's nice that it doesn't affect the jump height. That's amazing.
Have you done any characterizations of force versus time during the launch?
No, unfortunately, I don't think so. I don't think we have. That'll be really interesting to see. Maybe in the future we would do something like that. So that's a good idea. But no, we haven't done anything like that yet.
It would seem like you could probably just put a simple accelerometer on the nose cone and record that information, or telemetry it back.
Yeah, we could probably do something like that. So I would definitely give you some information there. So actually related to that is the other thing we're talking about is how to improve the spring design, right? So material the upper bound for how much energy you can store is about 8,000 joules per kilogram. But as you notice in the plot in the previous slides, we only go back to 2,000 joules per kilogram. And then also further than that is if we notice that these jumpers don't even use all that energy because they take off before the spring is fully straight. So then the question is, how do we get close? How do we maximize the energy we extract from these springs, right? So it turns out dynamics of the springs are important, especially when your jumper is mostly springs. So one idea is instead of having that one truss, is we have multiple smaller trusses, and that just limits the dynamics of, the inertial forces that the foot experiences. So we did some simple calculations, and it turns out that the more trusses you have, the more energy you can extract out of the jump height. So this blue area in this plot is how much energy you lose from just taking it off early before the spring's fully straight. The yellow area is how much Y kinetic energy you have in the Y direction, and then the green and purple are just like rotational and other translational kinetic energies. And then the line that we really care about is this black line, which is the average center of the center of mass Y kinetic energy. And yes, it turns out the more, well, at least according to our simple calculations, the more trusses you have, the higher you would jump because of because of later takeoffs and less inertial force, less extraneous force and less extraneous energy in non-takeoff directions. So this is an area of ongoing research. So we're trying to see what other tricks we can play to get even higher jump heights. So we can conclude with this video, a slow motion video of this jumper jumping. So we got this fan right here. I don't quite know how fast it's spinning, but it's going quite fast. And this is illustrating how fast this thing takes off. So any thank you for listening. Any final questions? Oh, any questions?
Outstanding presentation. Thank you.
Thank you.
Yeah, thank you. It was excellent.
Yes, thank you very much. I wanted to mention that for your Vine robots,
Yes.
I was thinking you could imagine brute force having a 3D printer inside a tube, and the 3D printer would be printing new tube. And then by controlling how the 3D printer printed the tube, the new tube as was being created could be stronger on one side or whatever it would take so that it would go in the desired direction at the point where the tube that's being manufactured would eventually get to where it would be, at the point of extension. But you could also imagine having a reel of deflated tube that you could then feed through the center, and just before it left the nozzle, you could make changes to the tubing so that it would go in the desired direction at the point where it got out to the point where it had folded out. Did that make sense?
I think so. Let me see if I can answer your question. So I guess like the 3D printed stuff is actually, yes, people actually have put like 3D printers on the tip of a robot to grow it. But I think you were imagining something more at the base, the 3D printer at the base, or is that?
Well, at the point where it's mounted, right? You have to mount the base of the Vine on the robot somewhere, or on the base. Yeah, on the base. And then just inside of that, you could have a 3D printer so that you'd be creating new tubing that would be then fed, by air pressure or whatever.
Oh, I see. Yeah, I mean, that'd be cool. I mean, that'd be pretty cool to create new tubing of via a 3D printer, and you get like the custom.
But it might be more efficient to just have a reel of deflated tubing on the base and you would unreel that and modify the tubing just before it went through the base, right? You could modify it with the anticipation that by the time it got extended out to where it would be folded out, it would be the right shape.
Yeah. Okay. So I don't think anyone's really done modification, like on-site modification, but there have been papers out there where people modified the tube already, and then it gets and you form the desired shape upon deployment. So no one's like actively, like, I don't think anyone's like deploying a robot and then actively modifying the potential shape of the robot, but there's definitely people who've already modified the shape of the robot and then deployed it. So.
And you could even imagine, you didn't mention anything about like a searching robot where you would want the vine to extend in some direction and decide on the basis of some sensors that you would want to reel it in and modify it and go in a different direction. So you could imagine doing that with some sort of tubing that in some way you heated it or slashed it with a knife or something, modified it so it would go in a different direction each time you send it out.
Yeah, I haven't really thought about it like doing it that way. I mean, people definitely, like, we've people taking these to like archaeological sites and stuff, but they were controlling it because they had a camera and a tip and they were just changing direction. But I don't think anyone's really deployed it and then retracted and then modified the shape. It's always more of like active steering with like these muscles.
So you've definitely got at least two different kinds of vine robot. You've got the kind where you have to somehow modify the shape in order to go in the direction you'd want to go.
Yeah.
And then you've got the other kind that you showed later where you're making use of the ground that you're going through to constrain the robot into a certain path, right? You're modifying the ground with your air pressure so that it goes in the direction you wish, and then you rely on it staying that way as you continue on to later points. Right?
Yeah. So that example is a bit of a hybrid. I mean, for that example, hold on, let me pull that up. That slide. Yes, so you are modifying the ground with like this airflow to keep you on the ground, but you're also you have to actively change the robot by having these tendons. So there's these strings over here that when you pull on it, it changes the bending of the robot, so it does steer it for you. So
but the point is that as you're going through the ground, you're steering the tip, but you're depending upon the ground to maintain the track that you did before.
Yes, that's correct.
You couldn't do that in midair. You'd have to have something around like the ground to keep it from the previous part of the vine from moving.
Oh, got it. Yeah. You can't do that in midair. There has been work on people have done work on shape locking the robots. So there's some mechanisms like a layer jamming. People have done like layer jamming type mechanisms where you have a whole bunch of strips of I guess like not strips of paper, but strips of material along the robot, and then by applying a vacuum to it, it's like a bit of like a telephone book effect, right? So you can't really pull them apart, so you get some shape locking from that. And then one of my colleagues have looked at using like melting and freezing polymers to do shape locking. And there's also quite a bit of other literature out there about how to lock the shape of the robot.
But by the telephone book, I don't know if everyone's familiar with that. If you take two telephone books and merge them together like shuffling cards, and then pull on the spines of the two books, you will not be able to pull them apart. That's what you're talking about by the telephone book effect?
Yeah, it's similar. It's similar. It's similar to that. Yeah, but I guess it's the way it's a little different. I guess like that's how you can imagine how the layers are arranged, and then you can enhance that effect by applying a vacuum to it, right? Once you apply a vacuum to it, you have the air pressure pushing on each of the layers, and because you have multiple layers, you have all these different interfaces with high friction.
Right.
So you really just can't really deform that shape then, because it's so there's so much friction, you just can't deform it.
Right.
So
Well, very
yeah,
cool.
so that effect is called layer jamming. If you guys are interested, it's very simple. Like it's very simple to do, and it's pretty cool. So cool. I guess, is there any questions from the chat or anything? So how slow do you want the robot to move? The air bladder robot should be able to move a lot faster.
I was mentioning that when he was suggesting using 3D printing at the tip, is our 3D printers right now are pretty darn slow. So I would think you'd want your robot to move faster than that. And that's where your air bladders move a lot more quickly. But perhaps there's other types of 3D printers that he's seen that I haven't seen that are faster. But
no, I'm saying that brute force, that was the conceptual way that you could make this robot that generated a custom tube at the base of the robot, with anticipation that by the time it got inflated out to the end of the vine, it would be the right shape. But like you say, it's slow. So then the next step is to say, well, have a reel of deflated tubing that you somehow quickly modify at the base, so that when it gets out to the place where it's deployed, it's the right shape.
I see. How many tendons are there in the air bladder soft robot that you showed that has the pictures? I only see 2 in this image, but I'm just curious, you only need 2 for good directional control, or do you need more than that?
All right, so this is not like, so I think there's three tendons. One, so you need 2 to get 2D motion, it's 3 to go up and down. So there's 3. I think there's 3 tendons, but I gotta check on that. So this is the work that some of my colleagues did, but I'm not quite sure how many he used. But I think there's 3 in this one.
It looks like near the tip there.
Yes.
There's the 2, it looks like there's a ring of gray with a ring of black around it.
Are you talking about this part?
Right there. That looks like a ring that's being pushed down by the pressure between the deploying tube and the center rod, right? So that ring gets pushed down as the vine grows.
So it gets pushed
along, right? So that it stays at the tip.
Yes, it does get pushed along. Yep.
It's getting pushed by air. Yeah, you can see growth air pressure. The top arrow and the growth air pressure there is in order to advance that ring.
Yeah. I think so.
I guess it's actually the top gray arrow from growth air pressure. You can see it goes in the central tube, or between, that one there. You see that air would advance the ring.
Yep.
By expanding the tube as it approaches the ring there.
It looks like
Although that gosh, I can see that there's a problem with that, because the tube wants to be the diameter of the outer tube, the already deployed tube. So if you put too much pressure on that tube, it might expand to that diameter, and then there'd be friction between the advancing inner tube and the already deployed outer tube.
Is there friction?
So right now your inverted body material,
Right.
it looks considerably smaller diameter than the outer body, right?
Yes, yes, okay, yes. So that does happen. Like, yes, if there is too much, yes, there is that sliding friction that does limit how far. Yes, so if your pressure is very high, it does. Yes, there is a frictional effect from the sliding over there.
And as I'm thinking about that, I'm wondering if it's possible to develop a body tube structure that would be stronger when it's inside out than when it's the right way out, so that it would want to be a smaller diameter before it's deployed. And then it would become easier to be a larger diameter once it's everted, right? Once it's turned the right way out. So I don't know what that material would be, but you could imagine, I would think, like a bimetal strip, something where you have dissimilar strengths of materials in such a way that when it's inside out, it's stronger than when it's stronger around the diameter of it than when it's turned the right way out, then it's a little less strong, so that it wants to be a larger diameter.
Huh. That is an interesting thought. Yeah, I'm not sure how yeah, I mean something like that might be possible. It might be possible. I guess the real challenge is to develop that material. It has to be super thin, because we want these things to be flexible.
Right.
And yeah, I'm not really sure. I think we would, that's something we would look into. We should look at, we would probably look into. Yeah, would. Yeah, that's a great thought.
Okay, folks, I'm going to jump in here real quick because I've got to depart in a bit. We'll keep the meeting running. I'll hand that off to somebody else to be a host if people want to keep going. Charlie, thanks for the presentation. This was great. And you folks can keep asking questions. At this point, I'm going to go ahead and stop the recording though.